Hey guys, so we're gonna look at some trig concepts from last year. You can ignore this warm-up problem. This should be a pretty quick review. You did this in year 2 and you did this last year, but we're gonna just start our trig unit off with a nice easy review. Trigonometry is a study of relationships between angles and side lengths of triangles. So today we're going to look at the easiest case where we're looking at right-angled triangles. So you remember each triangle has each right triangle has two other angles that are not right-angled. So suppose this was our angle. Remember, we would call this the opposite side. The one across from the right angle is the hypotenuse. The third side is the adjacent. Or if we had chosen this to be our angle we're talking about, opposite is right across from the angle, hypotenuse always across from the right angle, and the other is adjacent, the one touching the angle is not the hypotenuse. And we look at ratios of these side lengths because any other right triangle with that same angle will be similar to the one that we're talking about, and so the ratios of its side lengths will be constant. So in any triangle, the sine of the angle theta is defined to be the ratio of the opposite side to the hypotenuse. The cosine is the adjacent to the hypotenuse, and the tan is the opposite to the adjacent. And you can remember this SOHCAHTOA if you like. SOHCAHTOA, SOHCAHTOA. So let's calculate the trig ratios of this triangle below. So sine of 30 degrees, 1/2. 30 degrees, opposite hypotenuse. Cosine of 30 degrees is √3/2. And the tangent of 30 degrees is 1/√3. Easy peasy. Now let's use this information for something. Let's check this one out. Let's find the missing side lengths and angles here. So we actually do not have enough information to do this, but we could do it in terms of x. We can't actually solve, but we can write the others in terms of x. So for instance, the sine of 30 degrees we know is 1/2. It's also, let's call this side z and y. It's also opposite x over hypotenuse z. So z, 1/2 is x over z. Therefore, z, if you solve for z, you get x/2. So this is x/2, which makes sense. We know, z is 2x. And that makes sense because we know that this side in a 30-degree triangle, 30, 60, 90, has to be twice this side. So this should be 2x. Okay, and same here, cos 30 is y over z, but cosine of 30 is also √3/2, is y is 2x over, z is 2x, y is y. So y is 2x √3/2, which is just x times √3. So this side is x √3. Okay, now let's actually do one where we don't know we have enough information to determine the missing side. So we want to know this side. Let's call it y. So y is the adjacent, and we know, we want to solve for x. X is the opposite, and we know the hypotenuse, and we also know the angle, 53 degrees. So we can relate those three pieces, two knowns, one unknown, with sines. The sine of 53 degrees must be the opposite with hypotenuse. So x is 15 times the sine of 53, and let me get my calculator, and I'll tell you what that equals. 100-degree mode, sine of 53 times 15 is 11. Rounded to 3 sig figs, it's 12.0. The final situation we're interested in is if we know two sides, can we determine the angle? And yes, we can, because we notice that the tan of this angle is 5/4, and your calculator has stored the angle that corresponds to a tan of 5/4. The way that button appears in your calculator is inverse tan, and remember that's also called arctan, whichever you prefer. And again, we can put that into our calculator, arctan of 5/4, and we get 51.3 degrees rounded to 3 sig figs. Right. And so these inverse trig functions are inverse sine, inverse cosine, and inverse tan. Thanks, guys. Let's look now at non-right angled triangles. So for that, we can use sine law and the cosine law. So here, let's look at this non-right angled triangle, and note the customary way of labeling it. The angles are given capital letters, A, B, C, and then the side lengths. So the side length across from angle A is called little a, the side length across from angle B is little b, and the side length across from big C is little c. And the law of sine, what the law of sine says is that A over sine A equals B over sine B, which is equal to C over sine C. And you could prove this quickly if you wanted to by turning this into two right angled triangles and setting H equal to each other, like deriving H using this triangle, an expression for H, and then using this triangle. But we'll look at that when I get back. For now, why don't you just accept the law of sines? You should have seen why this is true in year 2. And the law of cosines is another law that relates angles and side lengths of non-right angled triangles. It will work on a right angled triangle as well. And if you pick one side, let's say A, remember A squared, it starts off like the Pythagorean theorem, but it's a little bit times the cosine of C. That is the law of cosines. You've seen why this is true in previous years, but I'm happy to discuss it with you when I get back. And you might wonder, when am I going to use any of these laws? Well, the sine law you can actually use in the cases ASA or SAA, which means two angles on one side are given, whether or not the angle is between the side or not, or the side is between the angles or not. The cosine law is used when two sides and an angle between them are given, SAS, or all three sides are given, which is called SSS. So we could use these laws. For instance, here are some non-right angled triangles. Let's pretend we wanted to find this angle, angle B. Well, we know this right away. Well, according to the sine law, the sine of B over 3.6 is the sine of 100 over 5. Remember, when you have pieces of information across from one another, the sine law is often quite useful. And I'm just going to remind you guys, the sine law, both of these two things are true. As long as you're consistent with whether angles or side lengths are on top, both are true. So whichever is more convenient for you. Sine of B is 3.6 times sine of 100 over 5.1, which is equal to, let me put that into my calculator, 3.6 times sine 100, which which is 0.695 if you go to 3 sig figs, and b is the inverse sine of 0.695. And now you would actually get two answers in the future when we take an inverse sine of an angle, but for now I'm just going to consider acute angles. 45.0 degrees rounded to 3 sig figs. So that is an example of the sine law. Let us look at example 2 now. Here, we don't actually know two pieces of information across from each other. So the cosine law is the law to use. This is SAS, side angle side, which is side angle side, which is a cosine law case. So cosine law says x squared equals 22 squared plus minus 2 times 22 times 28 times the cosine of 97 degrees. And that would make x is the square root of all this. If you square root and square root, x is, okay, let's see, second, put it in my calculator, 22 squared plus 28 squared minus 2 times 22 times 28 times the cosine of 97. I get 30 rounded to 3 sig figs, 37.7. Okay, so that is the cosine law. So I'm going to leave you to do homework. You want to do, for both these homework to cover both these worksheets we just went through. You want to do the right-angled trigonometry worksheet and the sine law / cosine law. Thanks.